Hello, today I'm just going to quickly be revising what we've learned in class, and we'll just be taking pipeline problems. Let me first start by saying this: all pipeline problems involve Bernoulli's theorem. All. And what is Bernoulli's theorem? That is the theorem of addition of energy heads. How do I put it? Okay, you remember this formula: Z1 plus P1 over W plus V1 square over 2G is equal to Z2 plus P2 over W plus V2 square over 2G. Do you remember this formula? If you do, this is a formula that just simply states Bernoulli's theorem. Now, all pipeline problems involve Bernoulli's theorem. So now, how does this theorem apply to pipelines? How? And I'm just going to quickly go through it. In pipes, like when we have a system like this, sorry about the diagram, and then the tank has an outlet of a pipe this way, there are losses that occur, as we have learned in class. Losses occur in pipes, like losses occur when fluids move through pipes. So now, what can be the loss here? We can have two types of loss. The first one is shock loss, and the second one is friction loss. Okay, so now how do we now relate the shock loss incurred and the friction loss incurred to Bernoulli's theorem? How? And this is how. Let us write that Bernoulli's equation again. I'll write it: Z1 plus P1 over W plus V1 square over 2G will now be equal to Z2 plus P2 over W plus V2 square over 2G. And this is it. Let us assume that the shock loss is given as HS and the friction loss is given as HF. We add it plus HS plus HF. I'm sorry for not explaining this earlier or stating this earlier. This first part of the equation and this second part of the equation relates the first, how do I put it, the pressure or the energy between this free surface and this place where the pipe is pouring out. So this first part is this place and this second part is this place. Now you will know that all the losses, they will cause, okay, if this is the total, the loss HS will remove from this and the loss HF will remove from this to give us whatever energy that we will have here. So basically the total energy here is an addition of the energy here plus the losses that have been incurred while the fluid was moving through this pipe. So as I said earlier, there are two types of losses: shock loss and friction loss. For the purpose of this crash course or this class, I will not be explaining both. I will only be explaining friction loss. And why? Because I have noticed that in our notes, shock losses are usually ignored. So only friction loss counts. And now, what is friction loss, or how do we get friction loss, or what is the formula for a friction loss? There's actually a way to prove the formula for friction losses. However, I will not be proving it here, but I will make videos later that will explain in details all these things. But we have a test by 5 o'clock, so I will just quickly explain what I can in this video. Friction loss is given by the Darcy formula. It's given by the Darcy formula, which says that the friction loss HF is equal to 4FL over D multiplied by V square over 2G. 4FL over D multiplied by V square over 2G. So now, where do we go from here? How does this relate to what we were given in our note? And how does this relate to what we were given in our note? All this, how? So let me just try to explain as best as I can. So when you have a pipe like this, assuming now, and you have the fluid, something like this, just for a short distance of the fluid. This is length L. The diameter of the fluid is this. That is the diameter of the fluid. And the velocity at which the fluid is moving, let us take it to be V. You will wonder how this is gotten, and I'm not going to prove it. But basically, this is length L of the fluid, the diameter of the pipe is D, and V is the velocity at which this fluid is moving. V is the velocity at which the fluid is moving. So now, we have this formula, HF, and that is the friction loss. How does it relate to this? Okay, you can see that it actually relates to this. 4F1, I'm now here, 4F1 L1 V1 square over 2G D1. You can see that that is the same as this. It's just that F is F1, L is L1, V is V1, and then D is D1. And that is because in this system that was used as an illustration in our note, we had 3 pipes, pipe 1, pipe 2, and pipe 3 joining together, making a sudden expansion. Okay, so now the total head lost is given by HL is equal to total loss. So in this case, HL will be equal to, okay, wait. In the case of this system that we have here, according to our note, let me first say that there are 2 ways that a fluid or that pipes can be joined together, in parallel or in series. This is a parallel connection. The one shown in our note is a parallel connection where you have the tanks, something like this, and then you have the outlet like this, and there's probably a sudden contraction over here, and then another contraction till you get to the second tank. This is in series where the pipes are something like this. Let me draw it. This is series connection, while parallel is when this is series. Parallel is when you have the pipes like this connecting the 2 tanks, something like this. So this is parallel. So basically, if you have two tanks connected in parallel, you will have them somewhat like this. This is a pipe and this is another pipe. These are two pipes connected in parallel. But let us first go through the series connection and how to get the total formula for any number of given pipes. So let me draw the pipe again. Now we are going to be considering two pipes connected in series, something like this, connecting two tanks in series. Both of these have, okay, I forgot to say what F is. F is the frictional coefficient in this formula here. F is the frictional coefficient. So both of these pipes have frictional coefficients. This one has F1, this one has F2. The length of this pipe is L1 and the length of the second one is L2. The velocity of this first pipe is V1 and the second one is V2. So now how do we find the total head loss? It's simple. HL will just be equal to, we know that our general formula for head loss due to friction is 4F1 L, sorry, is 4F L over 2 over D multiplied by V over 2G, V square, sorry. So now for the first one, for this first pipe, it will be 4F1 L1 over D1, where it has a diameter of D1 and this one is D2, over D1 multiplied by V1 square over 2G plus the second one plus the head loss due to friction in the second pipe, which will be 4F2 L2 over D2 times V2 square over 2G, which is simply an example of what is stated above. So for the number of pipes that you have, like if you have one, if you have two pipes, if you have three pipes, depending on the number, that is the number of times you will do this. So it is just the friction coefficient for this one, length of this one, diameter of this one, velocity of the first pipe, then the second one, then the third one, for as many as you do. In series, you add the friction losses. But in parallel, they are equal. What do I mean? Let me explain what the parallel connection looks in parallel. Now I have this diagram here and this is our note. I hope you've read it. Now I'll just quickly explain what pipes do in parallel. In parallel, pipes are connected, pipes of different diameters and sometimes the same length, other times different lengths, are connected between two reservoirs like this or two outlets to increase the discharge. Now what does this mean? We know that the length of this pipe L1, the length of the first pipe, let us assume the length of the first pipe is L1, the velocity of the first pipe, that is this pipe, L1 V2, and then it has a frictional constant of F1, and then the length of the second pipe is L2 V2 as velocity and then F2 as the frictional constant. And the diameter D1 and we have D2 here. The thing is that the discharge is going to be different for both pipes if the velocity and the diameters are different. What do I mean? Q is equal to A times V, right? That's area times velocity. So we know that the area is made up of the diameter. So if the diameter of the pipes are different, that means that the discharge will be different. Please note that, put it in mind. So now, how do we now relate the friction losses? I forgot to mention that when two pipes are not in the same level, like when two tanks are not in the same level, this is tank A, tank B, they are not in the same level, the difference in their length is HL. That could be said as the total head lost. So HL, the total head lost, is equal to the friction loss HF in pipe 1, and is also equal to the friction loss in pipe 2, HF in pipe 2. HL is equal to HF and is equal to HF1 and is equal to HF2. Basically, that formula that we had before, we know that HF without any this thing normally is 4FL over D V square over 2G. So for HF1 will be equal to 4F1L1 over D1 times V1 square over 2G, and HF2 will be equal to 4F2L2 over D2 times V2 square over 2G. And since they are equal according to this expression, because they are connected in parallel, so total head loss HL will be equal to 4F1L1 V1 square over D1 2G, which will now be equal to 4F2L2 V2 square over D2 2G. That's the total, or not total, this is the equation. So for as many pipes that you have in parallel, they keep getting equal to each other. I hope that is clear. And then before I end this video, you would see this formula here, and it is equal to this too. Both of them are equal. And how is that? Let us go back to our general formula of HF. HF is equal to what? 4FL over D times 4FL over D times V square over 2G. So now, how do we get this? How do we get this big formula with 32 and the rest? It's very simple. Remember that for continuity of flow, the discharge is equal to AV, area times velocity, and just make velocity the subject of the formula here. V will now be equal to Q over A. Expand area. V will now be equal to Q over 1 over 4 pi this square. Is that correct? So if this is correct, now we have V square here, right? So square it. V square will now be equal to Q square over 1 over 16 pi square d raised to power 4. And that will just give us, let me write it again, V square is equal to what? 16Q square over pi square d raised to power 4. Now substitute into this equation here. HF will be equal to 4FL over D multiplied by 16Q square over pi d raised to power 4 times 1 over 2g. And when you simplify this further, 2 cancel 2 here, remainder 2, and then okay, so HF will now be equal to 32, that's 2 times 16, 32 FL Q square over pi, this should be square, pi square d is power 5, then g times g basically. So this is the formula here. There's nothing scary about it. Whichever one you can know it, but know that this equation and this equation are the same thing. I'm just going to take some examples later.